Hello all, this is Anil. So in advanced control system, this is the first video. In this video, I have included basic introduction on state space realization. So before going to state space realization, here I have mentioned some limitations in transfer function and how we can overcome the limitations of transfer function with advantages of state space realization. Okay, so just I'm highlighting here. So in transfer function, we define under zero initial condition. Okay, zero initial condition. Whereas state space realization is not restricted to zero initial conditions. Okay, not restricted to zero initial condition. Then coming to second highlighting is transfer function is defined only for LTI systems. Okay, you can pause the video and you can just note down. So I have highlighted here what are the important limitations we see in transfer function and what advantages are there in state space realization. Okay, in transfer function, it's limited for LTI system, whereas for state space realization, for all classes of system, can represent with state space realization. Okay, so linear, non-linear, time invariant, time varying. Okay, so all classes of systems can be represented with state space realization. Okay, so in transfer function, okay, we cannot get no internal dynamics. Okay, we cannot get internal, so no information of internal states. Whereas here, internal dynamics are revealed in state space realization. Okay, and next thing is, so here we have only in transfer function we have only output based controller design. Okay, controller design based on output only. Whereas here both both state and output based controller design is possible. Okay, now coming to here in transfer function, like in continuous case we have Laplace. Okay, in continuous case we have Laplace, whereas in discrete domain we have Z transform. Okay, first we have to do in Laplace transform, then we have to come to inverse time domain. Whereas state space realization is direct time domain approach. Okay, direct time domain approach, not needing any inverse transform to obtain response. Okay, so same also the one more advantage is same representation. Like in transfer function we have continuous Laplace, in discrete we have Z domain. Whereas here for both continuous and discrete we have same representation. Okay, and one more disadvantage of transfer function is like for MIMO system it's difficult, okay, cumbersome for use. Okay, so I have highlighted here the major limitations in transfer function and what are the major advantages with state space realization. Okay, now coming to this side, here I included here mathematical structure. Okay, here I included mathematical structure. So coming to transfer function, okay, we already know that transfer function like output by input. Okay, so output by input, output by input. So we write it in polynomial form. Okay, so polynomial, so P1 in S divided by polynomial P2 in S. Sorry, polynomial P2 in S. Or we can also write it in pole zero form. Okay, this is pole zero form. Okay, pole zero form. So the this video is mainly for state space representation. So how to we represent mathematically state space realization. Okay, so in state space realization, basically if the system is nth order, okay, if the system is nth order, we define it using n first order ODE. Okay, so we have n first order ODE. Okay, n, so first order, okay, ODE, ordinary differential equation. Okay, so this n first order ODE will be function of states and input. Okay, so function fn to fn, function of states and input, and output equation also function of states and inputs. Okay, like here we take like n greater. So here the condition is p has to be less than or equal to n for causal. Okay, for causal, like here also we get that we take like n greater than m. Okay, for causal, same way here also like greater than or equal to. Okay, so this is the mathematical representation of state space realization. Okay, once you solve number of problems, it will become habit for you. So if you see it first time, don't get panic. So I'm going to next slide. right? So in the previous page, I included like mathematical structure, right? So here I include here block diagram. How do we represent block diagram of state space realization? So transfer function is very easy, like output by input. So we represent it using block here. So this is the input and this is the output. Okay. Now coming to state space realization. So in state space realization, we have these two equations. Okay. X dot equal to ax plus bu, y equal to cx plus du. Okay. So this you have to remember. Once you solve number of problems, it will become familiarity for you. So how to represent block diagram? Okay, for this. So since if you are trying for the first time, just follow some simple rules. So it will make task easy. The moment you see equation right, focus on summing block. Okay, focus on summing block. Since we have here two equations, okay, here we have two equations. That's why here this is the one summing block and this is the one summing block. Okay, two summing blocks are there. Next step. One more thing you have to remember here is that, let me use different way. The moment you see derivative term, okay, the moment you see derivative term, focus on integrator. Okay, focus on integrator. The moment you see derivative term, take an integrator, and input of integrator will be derivative term. Okay, input of integrator will be derivative term, and output will be state x. Okay, so take it as first step. Okay, second, since you have an equation, so take an summing block. Okay, so I took a summing block here. Next step. To this summing block, there will be input and output. So the input will be right hand side equation. So this is your right hand side equation. Okay, give it as input. Okay, this is the input and this is the input. Okay, and output you give as left hand equation. So what is your left hand? We have x dot. So the output will be x dot. Okay, now let me use highlighter. So input in with a with x. So we are accessing state x. We are taking block a that we are feeding here. Okay, and one more is b times u. So the input u, we're taking block b, and this is fed here, and output is x dot. So same x dot we have here. Okay, now coming to second equation. Okay, so let me use different marker. Right. So we have here output equation y equal to cx plus du. The moment you see one equation, focus on summing block. Okay, now focus on right hand side. Right hand, just feed it as input. So c times x. So we have taken here c, and this is the state x. Okay, c times x. And one more is input u and block d. Okay, from input u. So I have taken here block d, and it is fed as input here. Okay, and the output will be right hand side equation. Right hand side, what we have y. So the output will be y. Okay, which is the moment you solve few problems, it will become very easy. Since if you are seeing it first time, don't get panic. So the moment you see the equation, focus on summing block. Whatever we have right hand side, feed it as input. Whatever we have left hand side, just feed it, take it as an output. Okay. The moment you see derivative term, take an integrator. Okay. It's very simple. Next, I included here definition of state. Okay. It is a standard definition. In any book, you can find this definition. So what is state? It is minimum information of states. Okay. At initially T0, at T0 minimum information. So together, okay, together with knowledge of input for all t greater than T0 to predict the behavior of the output of a dynamical system for all future time t greater than T0. Okay, this is the standard definition of state. Just pause the video and read it 1-2 times, you'll get the definition. Okay, so next here is in how many ways we can realize the state space realization. So first I have highlighted a system dynamics. If you know from system dynamics how you can obtain the state space realization. Okay, the next video will be based on this only. So upcoming videos. So initially I take state dynamics and how we can obtain state space realization. Okay, then if we have transfer function, okay, when we have transfer function, then how we can obtain state space realization. Next, if we have block diagram, then how we can obtain state space realization. Inverse way also. Suppose we have state space realization, then how do we obtain transfer function? Suppose we have state space realization, how do we obtain block diagram representation? Okay, these are the things I will discuss in the future classes. So as it is first class, I thought to include some basic introduction. Okay, thanks for joining. Thank you.